Okay, so let's get started. Today we're going to talk about transformers, which is perhaps the most exciting class of this entire course. Hopefully, it will be not as hard as you imagine to understand what a transformer is. So last lecture we were talking about attention in RNNs, and to do that we motivated this idea with the problem of machine translation, which is just taking a sentence in one language and mapping it to a different language, like English to Portuguese or vice versa. And then we saw also like how to decode these sec-to-sec models. We saw greedy search and beam search as two methods to do that. And then we talked about attentions per se. We saw that idea of creating the context vector by multiplying the hidden states by alpha weights. Okay. So transformers, they build on that idea. So they were still defined in the context of machine translation. And to motivate transformers, I'm going to present two major problems with RNNs. And then we're going to talk about the ideas behind the transformers, which is this kind of encoder-decoder architecture that still follows this same idea from sec-to-sec models, but now the encoders and decoders, they're fully based on the attention mechanism. And the attention mechanism that transformers use is called self-attention because it's going to be doing attention within the input sequence, and not with respect to another input sequence. It actually is going to do the same, the two things actually, as you will see. But the key idea behind transformers is this idea of self-attention. Okay. And then we combine multiple self-attention representations to make what we call multi-head attention. And after that, I'm going to show the architecture itself, what the encoder does, what the decoder does. At the very end, we're going to see how the transformers include position information in the sentence, because now these models don't have recurrency, so they don't process each element one after the other. They're going to process all the input sequence at once, which is one of the major advances of transformers for dealing with sequences. Then at the very end, we're going to see this idea of masked multi-head attention to train the transformers. Okay. So we are still in the same problem. It's machine translation. Input sequence X of size Tx, output sequence Y of size Ty, so they can have different sizes. And we want to learn a model that maps X into Y. Okay. So here is the same data set we had before. And why not RNNs then? So the two major problems with RNNs is that, first of all, they struggle to capture long dependencies in sequences. As we saw, they have that bottleneck in the middle, and then the decoder struggles to produce sequences because it has to do that one after the other. But that problem also is related to the fact that it's hard to parallelize these networks. So in practice, we kind of have some limitations in terms of size of data sets we can train these models. So because they are not as efficient as transformers, in practice, it takes very long time if you wanted to train them on very, very large data sets. And then in practice, they end up not working as well as we would imagine. So imagine, for example, a whole story, like once upon a time, blah, 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 blah. So if you want to model a whole book, for instance, you wouldn't be able to do that very well with RNNs. And then the transformer is born in this context. Okay, so the main kind of motivation here was to process sequences in parallel. And here it is. This is the figure of the transformer. We're going to open these boxes in this lecture, but right out of the bat, what you can see here is that this architecture has two parts. So there's a left-hand side, which is the encoder, and then there's the right-hand side, which is the decoder. And we can see that the encoder takes the inputs, and then the decoder produces some output probabilities with a softmax, okay? And what is novel here, perhaps, is that, well, there is an input to the decoder that is not only coming from the encoder, but there is the outputs of, in the data set, the Y's are actually fed to the decoder, but shifted to the right, and you'll see why the model does that. But this is the famous figure from this paper, Attention is All You Need. This is a seminal paper, perhaps one of the most influential ideas in deep learning recently. I keep saying that, but yeah, in fact, these things keep happening, so it's moving very fast, but transformers are now everywhere in deep learning. They initially were designed for translation, but then very quickly people saw that they can be very general and solve all sorts of sequential problems. Okay? Even problems that weren't thought of as like sequential problems, when you model them as sequences and use transformers, the transformers get good performance out of it. Okay? For example, computer vision. So computer vision traditionally wasn't thought as a sequential problem. People would think as an image as one unit of a thing, but now you can see an image of as a sequence as well, of like image patches or just pixels if you want. And then all of a sudden you can use transformers as well. Okay, so I want to start by kind of showing the high-level contrast between RNNs and transformers, particularly for attention. So here you see a line dividing the encoder at the bottom and the decoder at the top. So both models have encoders and decoders. Okay. So here is our RNN with the Baranau attention, which is the attention mechanism we saw last lecture. So as what the encoder does, it processes the X inputs, right, from 1 to Tx, produces an edge state or a hidden state for each of these time steps, and then associates an alpha weight for each of these hidden states, produces a context vector, and that context vector is used by the decoder to produce its hidden state S, right? And concatenating it, the CT with the previous y hat t minus 1. This is the model we saw last time, okay? Nothing is different here. So here is the transformer. Look at the encoder. We still have the inputs here, so same thing, right? X1, X2, up to Tx. We're going to still associate an alpha value for each of these inputs. But now we don't have the hidden states. And this is one of the major improvements, because now we don't have that recurrency anymore. We don't have this for loop here over time. Okay? So somehow we're going to just directly combine these inputs to generate a context vector. And then the decoder is similar to produce. We're not going to call this a hidden state anymore, but just to do a parallel with RNNs, we could think as the decoder as having a hidden state S, which is formed by looking at the previous outputs, y hat 1 all the way to y hat t minus 1. So now I'm actually looking at the previous sequence, not only the previous word, but all the previous words up to now. I'm going to build also a context vector for that. So I have two contexts now. I have a context coming from the encoder, but the decoder also builds a context every time step for the previous word it has decoded so far. Okay? And then it produces the output. it's hard to draw a parallel in a very, without making compromises, because first of all, the transformer produces every time step at once. Okay? So it's going to do all the T's at once. And this is the key challenge here, is how do we do that? So imagine you as a researcher, you had this task, okay, you have to unroll an RNN with attention, okay, and produce or translate one sentence to another sentence just as a forward computation, okay? You don't want to have a loop for each word. So that's the tricky part here. So I think that's what's make the transformer not as intuitive as the previous models. But anyways, at the end of the day, we're going to produce a context vector for the input and a context vector for the output so far. Okay? But the way we compute the context vector, or the formulation, is the same. Is the weighted sum of the words that we had. But in RNNs, the words are represented by their edges. So you see here edge in the formula. I'm going to use the mouse so people see remotely. So on RNNs, the words are represented by the edge vectors. But you see here the difference in transformers. The words are represented by this V vector, which we're going to see in a minute. But I also have the alphas here. So I have the same idea of producing a weight for each word, and then which is going to tell me how much I should attend to that word T prime. Okay, so the overall idea is the same. It's just like an RNN without a for loop. Okay, and then the tricky part is, okay, how do we do that? And formally, we call the attention mechanism of the transformer is scale dot product attention, as opposed to the original attention, which now is called the Badenau attention, because the way we compute the alphas here is going to be different. Okay? So on the left-hand side here is the original formulas we used for the Badenau attention, same as before. But look at here, now on the transformer, we also produce an alpha T prime that is also softmax, because we need to normalize these weights. Same thing, okay? But here, first difference is how I divide here the ET T prime by dk. So there is a scaling factor here. That's why it's called scaled dot product attention, because there is this division here. And the dot product part is because the ET T prime is computed by a dot product. And these terms Q, K, and V, they are produced from the input words X. Okay. Okay. So this is it. This is the transformer attention. Okay. I'm going to spend the next minutes and next slides trying to unfolding these ideas. So hopefully it makes more sense to you. First of all, what are these Q, K, and V values, right? They're somehow substituting the edge, okay? Because we don't have edge anymore. So we need something like edge here. And we're going to produce this Q, K, and V. They are all vectors. And I have one of these vectors for each input X, okay? So let's go slowly here. So here is as an example, we have this sentence, Lucas is visiting Rio in December. What we want to do is to produce that context vector C4, okay? And all the other ones are the same. They are produced the same way. I'm going to just focus on one so we understand what's going on. And so just as an argument, the key idea behind transformer is this idea of self-attention, which uses that scale dot product attention. And it's called self-attention now because we're going to attend to ourselves. So think about this input sequence. we're going to find a way to represent a word looking at its neighbors. So that's why it's self-attention. The sentence is looking to itself. Okay? So for example, the word Rio is going to be encoded looking at all the other neighbor words. That's why it's called self-attention. Okay? So it's going to learn that context vector for each input element xt based on the input sequence itself. So that's why it's self-attention. So first thing we do when you're processing a input sequence is to generate this q, k, and v values, or values, no, this is our vectors, sorry, for each of these words. And the way we produce these vectors is just by multiplying them by a weight matrix. So we're going to learn these weight matrices. So see how key t prime here is equal to w key e t prime. And et, these e vectors, are the embedded vectors. So we don't, I'm assuming here we first computed the one hot encoding, which is the O1, and then we had an embedding matrix, the same way we saw before, to get E1. So this is the embedded vector. E2 is the embedded vector. So using these embedded vectors, we multiply them by 3 different matrices, each one of them. So then each one of them have these Q, K, and V vectors. And the names here comes from query, key, and value. It's kind of to an analogy as a database type of thing. Okay? Don't worry too much about that. But is this clear so far, what we are doing? Okay. So now, similarly to the Badenau attention, we're going to produce alpha weights. And here is actually simpler. We're going to produce alpha weights by just doing a dot product between Q and K. So note how the query here is the word Rio. So I have Q4 in each one of these dot products. Q4, Q4, Q4. So what I'm doing here is, okay, I want to learn a representation for the word Rio. And so I make a query out of this word. And I have each one of my neighbors as keys. So Q1, K1, K2, K3, K4, K5, and K6. And remember that the dot product can be thought of as similarity. Okay? So the idea here is I'm going to compute the similarity between each word, or between a word and all its neighbors. Including itself, right? So then I have the alphas. So, and I do the same as before. Now I multiply the V's by the alphas, but that's it. I multiply the alphas by the V's, and then I get the same type of attention. Is a weighted sum of V's weighted by alphas. And I do that in parallel for each of these, for each word. Okay? I do that at the same time. And this is the hard thing to visualize, right? All these things are happening in parallel. So I'm doing the same operation for the word Lucas, then is, then visiting, then Rio, then in, then December. And at the end of this parallel operation, I have a C1, C2, C3, C4, C5, and C6. Okay? But that's it for self-attention. And this is the key idea behind transformers. This is what makes it work, actually. And to be honest, it's simpler than the Badenau attention, right? Because we don't have that fully connected layer here. It's just a dot product. Okay, but there's a little more, right? First of all, let's understand these matrices, or these Q, K, and V values a little bit more, okay? So when you have self-attention, the input is a sequence, which you can think of, so the input of the self-attention is this E sequence, right? E1, E2, E dx. And the output has the same number of elements, but now transformed with contextual information. So C1, C2, C dx. So you can see that E1 was transformed into C1, E2 was transformed into C2, and so on and so forth. But now these C vectors, they are contextual representations of each of these words. These are the embedded words, right? So this is just ET, so it's clear, it's just WE times OT, right? Where O is the one hot encoding. So ET, this is the embedding matrix, right? So we know that this representation, even though it has that property of putting words that have similar meaning in the closer in the space, it's still like a static representation. So it's not adjusted to different contexts. As we saw, like the word apple, if I have the sentence I work at Apple, or I just ate an apple, so this representation E for the word apple would be the same if you just had this layer. But now we are transforming with self-attention, we are transforming that embedding representation using attention. And now all these C representations, they are kind of like stronger representations because they have context in them. Okay. And they'll depend. So if the word apple was here, this representation of the word apple is going to depend on the other words, right? So that's why it's contextual. So the way we compute this C representation is in a vectorized way, is by defining three matrices, Q, K, and V, but capital. So the Q matrix, for instance, has all the lowercase q's or QTs, right, in the rows. So Q1 is first row, Q2 is second row, and then QTX is the last row. Okay? So then we have the K and the V the same way. And we want to learn, the final goal of the transformer is to learn these three matrices. Okay? Because they are all initialized randomly. Okay, and we want to learn them through a loss function and gradient descent. And how do we use them? So we use them to produce the attention for all the words. So here's our softmax that people are asking. It's typically applied in this vectorized way. But the formula is the same, right? QK, you can remember this is the dot product. This is the dot product between Q and K. This is the similarity part. It's transposed now because to make the multiplication work. But the Q times K is just the alpha part. We divide by the square root of dk. Dk is the dimensionality of K. Okay, but that division there is the scaled part. So it's scaled attention. Okay, or scaled dot product attention. The dot product part is the the Q times K. So you take the softmax, and that becomes the alphas normalized. And you just multiply that by V. So here you have the whole, that same formulation of a weighted sum, but in a matrix form. Okay? And yeah, I know it's hard to look at these equations. So here's an example, okay? Here I have a sentence that is shorter just for the sake of the example. I have 3 elements in the sequence, x1, x2, x3. So for example, imagine I love teaching. I don't know. And I want to encode that sequence. So I produce the Q, K, and V for each of the words x1, x2, and x3. So here's my Q matrix. Okay, I just stacked those 3 blue vectors in rows. And I do the same for the Q matrix, the K matrix. Sorry. But I transpose it. So I have a 3 by 4 matrix and a 4 by 3 matrix, right? So the result is a 3 by 3 matrix, right? And these are just attention weights unnormalized. So they are not normalized, but they are attention weights. They are like the E's, okay? They're not alphas yet. So first divide this by the size of K, and this is just a division element-wise, okay? You divide each of these numbers by that dk. Dk is a number, by the way, it's not a vector, okay? So, and then I take the softmax. So now I have, look at the rows. The rows are all normalized, right? They sum up to 1. 6 plus 2 plus 2 is 1. 1 plus 7 plus 2 is 1, okay? So now I have the alpha weights there in that purple matrix. So you can read this as the attention weights of word I in the row to word J. So you would have Lucas loves teaching, I love teaching in the rows, I love teaching in the columns. And if you look at let's draw this. So I love teaching. And then I love teaching. What you get is 0.6, 0.2, 0.2, right? 0.1, 0.7, 0.2, and then 0.2, 0.4, 0.4. So you can read this matrix as, if I was decoding the word I, I'm going to put 60% of attention on the word I, 20% on B, and 20% on teaching. Okay. And you should look at the paper. The equation is exactly like this there. Okay. I'm just breaking it down like visually here. So at the end, then you multiply by V, which is a 3 by 4 matrix, right? We took these 3 vectors, stacked them on rows, right? That's why K there is transposed, and V and Q is not, because the reference is stacking them on the rows. But then now you have a 3 by 3 matrix, then you multiply by a 3 by 4. So the result is a 3 by 4 matrix that brings us back to the original dimensionality. Okay? So look how C has the same dimensions as Q, K, and V. Okay? And C, you can see the matrix C as the contextual representation of the words on the rows. So it's a very clever solution. And the key idea here was to make this projection Q, K, and V using the dot product for similarity and then computing the normalized way. And well, obviously there is more, but this is the heart of the transformer. Okay, is the self-attention. So see that at the end of this layer, if you look at this as a layer where X is our input and C is your output, for each X I have one vector C. Okay. And again, what is missing here in these arrows is the E, right? So I don't work with the one-hot encoding, I work with the embeddings normally. But this really is just an extra thing, doesn't really add much here. Any questions? So now we're going to borrow an idea from CNNs, right? We're not going to learn one set of Q, K, and V's. We're going to learn multiple Q, K, and V matrices, as we did in CNNs. Like in CNNs, we learned multiple filters, right? Here we're going to learn multiple contextual representations. That's why the layer of the transformer is called multi-head attention. So head here is similar to a filter. A head is a C. A head here is one of these C matrices. I'm calling it CI now because I'm going to have multiple of these C representations. So basically, I'm going to learn different Q, K, and V matrices. Okay, that's it. So you can visualize it this way. I'm going to have more than one Q, K, and V for each word, right? And then this means, yeah, I'm going to have those weight matrices, WQ, WK, and WV to produce the Q, K, and V vectors, one for each of these heads. So now this is a three-head model because it had these three heads. And this is just to add more capacity or to learn different representations and then combine them, right? This is, at the end, we just concatenate all these things. Okay. Okay. All right, so let's look at the encoder now. Now we know everything that makes the transformer work, but let's see how it combines all these ideas. It's not everything, there's one missing part, or two actually. But what is important is, so the encoder takes a sequence X as input and outputs a contextual representation C, right? So it's going to learn multiple of them, but then at the end it concatenates all of them. So you can see this at the same way. Okay? It's going to be one C representation for each X word there. So the way it does that is it's going to apply this multi-head layer followed by a MLP or a feed-forward network. And then it combines this two layers with layer normalization and residual connection. So now we are bringing ideas from ResNet, right, and layer normalization. So let's go slowly. We started this sequence, X. So there is one part that I'm going to leave to the end, which is the positional encoding. I'm going to talk about this in a minute, but I'm going to produce a positional information for each of these words and sum this with my input sequence. And this part is fundamental because remember, we don't have recurrency anymore. So the model doesn't know, if you didn't have this, the model wouldn't know which word comes before or after. So then any permutation, if you didn't have this, any permutation of a sentence would be the same sentence, pretty much. Right? So this positional encoding is to include position information. And this is very clever as well. And this was one of the key problems. If you have to remove recurrency, this was one of the main innovations as well. But I'm going to leave this to the end because this is not very intuitive. But the rest is just application of what we just saw. So we start with the X sequence. We produce the Q, K, and V matrices. Okay, and I'm showing here the dimensionality of the sequence for each of these layers. Okay, so now at this point, before the multi-head attention layer, I had an embedded EX sequence, which is the embedded version of X with position information. But the dimensionality is the same. So just so we are on the same page, you could visualize this E vector like this. Let's say, I love teaching, right? So first, so you have the O, O-I, O, love. This is a one hot vector. Let's say we had a vocabulary of size 3. So this would be 1, 0, 0. This would be 0, 1, 0. This would be I love teaching. This would be 0, 0, 1. And now we have the embedding, which is not there, but we know how it works. It's just an embedding layer that gives us E1, EI, E love, and E teaching. Okay. So now I'm going to move it to here. Now I have positional encoding here. And this is the part I'm going to leave to the end. But I'm going to sum with this vector. So this is still a 1 by 3 or 3 by 1 vector. Okay? Each of these words are still a 3 by 1. Here it could be, here is a 3 by 1, but it's just an embedded vector now. So it could be, I don't know, 0.8, 1.2, minus 0.3. And here you have a dense vector, 0.9, 0.9, I don't know, 0.0. And here you could have 0, 0, 1. No, that's just 0, 0.5, 0.2. And now the positional encoding is going to produce a 3 by 1 vector for each of these words, and I'm going to sum. So at the end here, I still get 3 by 1 vectors, but now with positional information. And don't worry how we're going to actually make this for now. So this could be maybe, I'm not sure the math is going to be right, but let's say 3.5, 2.1, minus 0.3. And this one could be 1.0, 0.2, 0.1. And here it could be 3.7, 0.9, minus 0.1. Okay. So this is that EX. So this would be EX1, EX2, and EX3. Okay? So now, as you already know, after the multi-head layer, we produce the contextual representations. And now, as I said, we're going to add and normalize. So the normalization is a layer normalization, and we're going to add that EX with the C. Okay? So we do layer norm on C plus EX. C is a vector with TX elements, or is a matrix, right? But you can think of it as a sequence. So EX is a sequence of vectors. C is also a sequence of vectors. So you can sum C with EX, and then you get another C updated. And that goes into a feed-forward network. So for each of these C's, I'm going to apply MLP as input, right? And MLP takes a vector as input and produces another vector as output. And then I just add, again, C with F. C is coming from here, right? This is a residual connection. I'm taking C here, summing with F, and then normalizing everything. And that's the output of the encoder. Okay, so here's the decoder. So let's start with defining the inputs and outputs. So the decoder takes the context from the encoder and the previous produced outputs, y hat 1 all the way to y hat t minus 1. So we are now producing, with the decoder, we are producing the time step t. Okay? It's going to happen in parallel, but we can still think with time steps. And I think that's the hardest part to understand transformers, that these things are happening actually in parallel. Once you implement it, it makes more sense. But we want to output the next token y hat t. So here's we're going to feed this, all the decoded words so far. So all the decoded words. Imagine I already translated I love, so eu amo would be my y hat 1, and this is my y hat 2. And now I'm at the stage of producing y hat 3. So I have access to these words. And I have access to this context, C1, C2, and C3, there, coming from the encoder. So I'm going to do positional encoding for this decoder input, or to the previous words. And this is similar to what happens there, right? I'm just adding positional information to my decoded word so far. Now I have the same block of multi-head and residual connections, but there is a detail here. That layer there is not a multi-head layer, but it's called a masked multi-head layer. And this is more important for training. Okay, and so I'm going to leave this for the next slides. So far, just imagine this is the same multi-head layer. It's exactly the same thing, but with a mask. So it's the same idea. Okay, but we're going to see why we need to mask this in a minute. So this is going to produce an A vector with the same number of elements from 1 to t minus 1. Oops, sorry. Okay. Then I just connect them with residual connections. Again, remember the purpose of residual connections and layer normalizations. So residual connection helps us learning long, deeper networks. Okay. And the normalization here is also to make training faster. So these are mainly for that purpose. Okay. Now, this is the cool part, because what the decoder is doing is receiving the previous words as input in a form of a context. So remember, the multi-head attention makes a context for its input. So now it's producing a contextual representation for the decoded words and the input sequence. So that multi-head attention in the middle, or layer, is going to combine these two things and make what we call a cross attention. Because the V is going to come, or the Q and the V is going to come from the encoder, and the Q is going to come from the decoder. Okay? So as if I'm making a query for each decoding word, but the key and the values are coming from the encoder. Okay? So this is a cross attention. I am relating, if you want, this word with all of this tree, and then this word with all of this tree. So for each of these decoded words, I am kind of computing a similarity or an attention score between this and this tree, between this and this tree, okay? So I produce now this cross-attention vector that is the very last representation, almost the very last representation we want to use. So we just add and normalize again, right? That's the same thing, and add an MLP and normalization with residual connection same way, okay? So this top part of the decoder is exactly the same as the encoder. The only thing that is changing, so what it does is essentially the same thing. But this middle multi-head attention is correlating the decoded sentence so far with the input sequence at each time step. And this first bottom here multi-head attention layer is encoding, if you think of it, is encoding the decoded sequence so far. And that's it. We finally feed this to a feed-forward, to a fully connected layer just to produce a softmax. And that's a distribution over words. Okay. So it looks complicated, but it's a stack of multi-head layers. The yellow parts are just to make the network bigger. So the yellow parts are just like the cherry on top, right? It's not what really matters here. It's not the heart of the transformer. The heart, you see, is this multi-head, the red layers. They are what they are doing the heavy lifting, okay? And the smart thing to do here was to just process sequences with attention. At the end of the day, we removed everything. The feed-forward networks are just giving more capacity to the model. They're just adding more weights and making more complex representations, or making the vectors more, or learning more latent representations. But at the end of the day, the multi-head layer is what is doing the job here. Okay, so, and we can have as many encoders as we want on top of each other. We can stack these encoder blocks, and we can stack the decoder blocks as well. So you can have one encoder on top of the other, on top of the other, on top of the other, that goes to the decoder. You can have multiple decoders, one on the top of the other, until you have the softmax at the end. That's why you see this nx. So n times, and n is, you can pick the number of block, the number of blocks you want, both for encoder and decoder. And finally, that's it, except for the positional encoding and masked multi-head attention. So let me show an example, so you see how these things would play out. So consider this sentence: Lucas is visiting Chile in January. This should be the real example. I'm not going to Chile. But this is going to produce that EX representation with 8 elements, because there is 8 tokens in this sequence. Right? Let me count it here. 1, 2, 3, 4, 5, 6, 7, 8. So 1 for each of these elements. Then I learned the contextual representations, 8 elements again. Right? So everything here is going to keep that same dimensionality all the way up at the end. So then I have my Q and V matrices here that are going to be now multiplying the C vectors from the encoder. Okay. Now I need to produce the Q from the decoded sequence so far. But I don't have anything so far, so I start with SOS, start of sequence. Okay. So then I produce EY hat, so my embedded representation, there's only one element so far, right? Same for all the other transformations. So after the first multi-head attention layer, there is one element in the sequence. So A1 has only A11, A2 has only A21, and so forth and so on. Okay. So at the end, I'm going to have this attention structure or sequence with just one vector there. And I feed that to a fully connected layer and a softmax, and I get, hopefully, the word Lucas. Okay. So second time, what I do now is I concatenate that output back here, okay, and I feed that back to the model. So now I have two elements, okay, on each of these steps. And now the model is going to produce Lucas Ira. Note that because it's a parallel model, at every decoding step, it's going to give me the prediction of each input. So after SOS, it still gives me Lucas, and after Lucas, it gives me Ira. So I take only the last word there and concatenate back, and I repeat that process, right, until I finish with AOS sentence. So if you note, the decoded input is going to be one element to the left here. So it starts with SOS and then goes to Janeiro, and there it starts with Lucas and goes to EOS. So it's that sentence is actually one shifted to the right, right? Because I'm always predicting the next element. But I'm doing that in parallel, so I produce the next element for each input of the decoder. And that's how you use the transformer in practice. That's not how you train it, because that would require a for loop, right? I would have to do first start of sentence, then get Lucas, then concatenate back. That decoding step, when you have a trained transformer, you still produce the translation word by word. And that's why we call this an autoregressive model, because it takes the output, concatenates back with the input, and keep doing that. So this simulates the RNN. But the cool part is that we can train this in parallel without a for loop. And that's why we need this masked multi-head. I'm going to show you this. Oh, before let's just talk about positional encoding. I forgot about this. I thought this was the last step. But for positional encoding, we have to address the following problem. So the self-attention mechanism, it doesn't consider position of the words. It only produces these matrices, Q, K, and V, right? That formula makes sense, it's a weighted sum, but there is no information of position in there, and there is no for loop, so how come can I know which word comes after the other? So to add this information to the learned contextual representation C, both the encoder and the encoder, as we saw in the diagram before, it adds some positional information to its inputs X. And this is the part we saw, right? Right in the beginning of both the encoder and the decoder, I have the input X. I pass that through an embedding matrix E. And then I sum the embedded vectors with this positional encoding to produce EX, which now has magically positional information. So how does this positional information work? This is perhaps the least intuitive part of the transformer. Is they use sines and cosines to add position information to each input element of the sequence X. What you have to have in mind is that for each of these words X, here in red, so this is our embedded vector here. This is let's go back to this part. So the vector in red are these embedded vectors before positional encoding. So what I have to do in positional encoding is produce a vector in blue that has the same dimension of the X, but somehow adds position information to each element. And what they're doing is, if in blue here, right, if the index is odd, which is the first one here, I'm going to use a cosine. If it's even, 2, I'm going to use a sine. So each of these dimensions here are going to be alternating between sine and cosine. So the positional encoding output has the same length of the embedded vector. So if your embedding matrix produces vectors of dimension 3, your positional encoding also has to produce 3 values for each index of the vector. So let me show you this visually. What this is doing is, so I here, I is the index of the vector. So it starts with 0 actually. So 0, 1, 2, 3. Okay, 0, 1, 2, 3. So what you're doing, you're producing a sinusoidal function for each dimension of the vector. So this is the dimension I equal to 0, which is this dimension here. Dimension 1 is this dimension here. Dimension 2 and 3. So you produce a different sinusoidal for each dimension. And if I is even, you use a sine. And if I is odd, you use a cosine. And what you're going to do is then sample from the sinusoidal to add the positional information, like this. And it seems extremely complicated and unreasonable to do this. And the intuition here is that, at least the way I like to think about this, is maybe the easiest solution would be to add the numbers 0, 1, 2, 3 here. Right? Add the index. Why do you need to make a function of the index? Right? Why not, this is just 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, the number 0, 1, 2, 3, and then if you have bigger vectors, just 0, 1, 2, 3, 4, 5, 6, 7, 8, just incrementally adding by 1. Right? And I thought of this a long time, and that wouldn't be a good idea because the relationship between two words is the same. So if you pick a word I and a word I minus 1, the distance is 1. And here it's not, but it's still, it's predictable. It's not the same distance, but it's a predictable distance which helps the model learning position. So to me, this is the least intuitive part of the paper, and unfortunately, there's not much discussing this in the paper itself. Okay, I'm going to open it here before we finish, so you have a look at the paper. But essentially, what the function is doing is this. Okay, and if you had, let's say, if you had more dimensions, you just would have more sines and cosines with, and you would just add this information, these samples from these functions in order to your positional encodings. And it works because it's repetitive and predictable, but not just linear and infinitely increasing. Okay, let's just finish because I don't want to finish this lecture without talking about the whole thing, which is this is the last slide. So to train a transformer, we have this data set of inputs and outputs, right? And the decoder takes the decoded sequence so far. So in training time, right? In training time, I don't want to have that loop, that for loop that starts with SOS and then produces the next one and so on and so forth. So to simulate that, I'm going to mask my input to the decoder. Let me just combine these two things. So the training step is I take the source sequence X as input, and I have the whole answer at the bottom. So look at the bottom here. This is actually Y, not Y hat. So I'm giving the whole answer to the decoder, as if it had decoded everything correctly. Okay, so this is called teacher forcing. Okay, just another name, but I'm giving the answer to the decoder. But consider, for every prefix, I'm going to make a mask. So I want from SOS Lucas irá visitar o, I want to predict the next word. It's Chile. So what I'm going to do here is I'm going to mask the future. I'm going to just zero that. So as if my model had got everything right up to here, and it just had now to predict the next word. So this is somehow easier than what the sec-to-sec model was doing. Because the sec-to-sec model was predicting one word at a time and feeding the output of y hat t to y hat t plus 1. So if it got the t1 wrong, it would affect the decisions in the future. And now I'm not doing that. I'm actually giving the whole correct answer, and I'm assuming that the transformer is actually decoding them correctly at each time step, at least up to t minus 1. And then I just have to guess t from t minus 1. And just to make this more visual, the way you actually implement that is you keep this is the same masked multi-head or multi-head attention we had from before, okay? But there is one mask matrix you have to build. You basically just make this matrix where the first diagonal has, or the bottom left of the matrix has zeros, and the top right matrix has minus infinity. Because now when you apply the softmax, so first of all, when you sum the mask with the QK multiplication, because these zeros, this part doesn't change, right? So the bottom left doesn't change, it's the same. Sorry, this 16 here is because of the division here. Sorry. But you keep this part untouched, and the top right corner is masked. It's minus infinity. So then when you apply the softmax, the probability of those words go to 0. So, and the effect that this has is not letting the model attend to future words. So if this was I love teaching, I can only look at the word I. If for the prefix I love, I can only look at the word I and love. So I can only look backwards, because I actually erased the distribution of the future. Okay, and this is how you would train a transformer. And the main idea here is to avoid that for loop, is to be able to do this with matrix calculations. Okay, and that was it. Next lecture, we're going to talk about BERT and GPT, which are these famous architectures in natural language processing. They have different motivations. But guys, yeah, it's hard to really make sense of everything here. I'm going to point you to some readings. Make sure to do that. The one that is mostly important is the annotated transformer. This is a very famous blog post from Harvard. It's a Harvard NLP group. It was famously hard to read this paper, so especially to implement it. So this group at Harvard, they actually annotated the paper with code. So you can read the paper with PyTorch code. So they actually they copy the text from the paper and then just write the same thing in PyTorch. So they translate the English of the paper to code. Okay. So you see here that they take every sentence from the paper and they actually annotate it with, they explain and they implement it. So you can look at the formulas, look at the code, and then at the end you have a fully working transformer from the text of the paper. So this is not someone else's text. It's actually the explanation from the paper with code. So this is extremely useful. And here's the sine cosine part for positional encoding. Extremely, extremely useful. For me, this was perhaps the most important thing that helped me understanding the transformer, actually. So I'll link that on the website and make sure to read this question. Okay. Thank you. I can take questions now.